Okay, let's dive right into lens problems. Just like mirrors, lenses bend light. Lenses bend light. Hopefully you can see some strange bending of light going on here when I have my eyeball magnified. Anyway, let's get right into these. What's important to remember is sign conventions with these. Number one talks about uh, a lens that has a certain focal length, and it also talks about being a converging lens. That means that it has this shape, and then it means that it has this sign. So let's review our sign convention chart before we start these. Also, it says that the image shows up in front of the lens. In this case, images in front of the lens are virtual. Images that would show up back here would actually be real because light can actually pass through and form an image on a piece of paper. But in this case, this would be a virtual image. So again, check your sign convention chart for that. Other than that, it's a relatively straightforward algebra solving here. We just take our givens, plug them into the equations we know. We can solve for the object distance. How far away from the lens should this thing be? 6.31 meters. And we can also see that it has a magnification of 4. Now let's dive right into the ray diagram, okay? Lenses are different than mirrors in a couple reasons. Light passes through them, of course, but because they have two curved surfaces, they have two Fs. So we want to mark out two places, this many centimeters or inches, whatever you decide your scale model to be, and this many as well. So 6 inches away, 6 inches away, 4 or 4 away. They have to be equidistant from the lens. There's also a point C, which is represented right here, and that indicates the center of the lens. The ray diagram rules, as you saw in the notes, are parallel and then through F. The light keeps going through the lens. It doesn't bounce off. Then the light passes through this F and then parallel. And finally, the light passes through C. Light that passes through C passes directly through. These light rays don't actually meet to form an image. So what we have to do is we have to trace them back to see where that virtual image, where it looks like the light rays are coming from. If we trace back these three refracted rays, these three bent rays, we see that they meet right here. This is where we draw Q, and that represents Q, our image distance. Again, Q looks bigger than the object, and it should because it's magnified. It should also be a negative value because it's in front of the lens. Moving right along to problem 2, let's take a look. We have a different type of lens. We have a diverging lens, which is shaped like this. If you look at the sign convention chart, diverging lenses have a negative focal length. It also tells us that this image is formed in front of the lens, and so we would need to know that Q is a negative value. So it will show up here at some point. We need to plug it in as such to get the proper answers according to the answer key. Let's take a look again at how these ray diagrams work. Again, with this type of lens, light is not brought together, light is spread apart. So we actually have to trace it through a different set of Fs. Parallel and not through this F, that would be a converging lens. It's parallel and through this F now because we want the light rays to spread apart on a diverging lens. As you can see, this one is lined up as if it's going through F and then parallel, lined up as if it's going through this F and parallel. And finally, this one goes through C, right through the center. Again, these rays don't actually meet, and so what we have to do is trace them back. So we trace this, and this back to see where they meet. They form a virtual image, Q. Does that make sense? Well, it should make sense. It should form in front of the lens, and that's indicated by this sign right here. So we would know that Q has to be negative. Okay, I think those might be the two most challenging ones, but let's take a look at one more ray diagram that would show a different type. So far, these two have both been virtual images. What happens with real images with these lenses? Well, it's actually a lot simpler. In a real image, the light actually does come back together over here to form an image behind the lens. This is a point where we could actually put a piece of paper. If I had you in class, I'd do a little demo where we let some light pass through these lenses and show you that you got a little image of my screen or the window across the room or something. So basically we have parallel through F, and parallel, and then through C. Where the light rays come back together, we have Q. What would the sign of Q be? It would be positive here. What would the sign of these Fs be if we plugged them in? These would also be positive because this is a converging lens. So several of the problems will end up looking something similar to this. Don't forget about that simulation. There we go. So you can try to figure out to see if your answers make any sense by adjusting several of these givens on here. You can adjust F, you can move the object and the object to a different place, and hopefully that can help you verify whether you're correct.